कजरी
आपको भी ज्वाइन करना चाहिए। ये जूम मीटिंग में है सेंट्रल गवर्नमेंट का वो मीटिंग है अभी।
Everyone, today we are really honored as we have Kirti Avishek sir with us. He is a PhD and professor of Department of Civil and Environmental Engineering. Dr. Kirti Avishek is an alumnus of Dr. B.R. Ambedkar University, Agra, where he pursued his master's degree in environmental science during 1999 to 2001. He later pursued his M.Tech degree in remote sensing. After qualifying UGC NET exams in lecturership in 2002, he joined Birla Institute of Technology in 2004 as a lecturer. Dr. Avishek passed his PhD from ecosystem management and later pursued his postdoctoral from the Chinese in 2011, where he published two UNEP policy documents. Dr. Avishek has around 30 journal publications and several proceedings and book chapters. He has also published 4 books. His research interests include ecosystem management, topsoil management, wetland management, and catchment area treatment. He is an environmental consultant and has obtained consultancies from Adani Enterprise Chhattisgarh, CINI Tata Trust, Environment DAS Limited Lucknow, GMDC Gujarat, and CMPDI Ranchi. He is also pursuing research projects funded by IWMI Sri Lanka on drought assessment and UNICEF on water sanitation and hygiene. A passionate environmentalist who believes in action rather than words and has thus applied knowledge in his house, which is rainwater harvesting, has waterless urinals, reuse wastewater, and has adopted herbal gardening. Thank you, sir, for joining us today. Over
Thank
to
you
you,
so
sir.
much. Thank you so much for your kind words. And I would like to thank Sayad for giving me an opportunity to share my thoughts and my ideas in this platform on GIS. And special thanks to Bishwajit Roy in this regard. And I'll be starting my presentation. So keeping in mind the internet irregularities that may happen. So I'll be switching off my video and then move for the screen share. I hope this screen is visible to all of you.
Yeah.
Okay.
Yes, sir.
Okay. As it has already been introduced, I have interest in ecosystem management, which, if you see broadly, covers various aspects of science and research. But and I have been working on different issues of wetland or urban planning, and also on forest ecosystem drought assessment. But today, what I'm going to present is the most important, some of the important issues that we are facing every year, and a resource which is getting scarce with time and with years, and with the demand increasing. Either this resource is degrading with respect to quality or with respect to quantity. So both these aspects of water resources are getting affected, and that is why it's a prime concern that we need to do something about the water resource assessment and planning. So keeping this in mind, what I'm sharing with you is also an application where I'm trying to compare a normal numerical method system and a GIS method system. So, and how things will be varying that you can assess at the end of the presentation. Okay. Well, water is a very precious natural resource without which life cannot exist. It is a resource with almost fixed quantum of availability. The demand of fresh water is going up continuously with increase in population. And with continuous growth in the country's population, the per capita availability of utilizable water is going down to meet the requirement. As I was telling you, since we have been concerning about the water quality, there's another major concern that comes up is the water quantity. And if the water quantity is getting affected and further to increase the problem, you have water quality. So both these aspects needs to be assessed, and I have used GIS to replicate or depict some information through it. So the problem that has been identified is that water is a limited resource, and both the acceptable quality and quantity is required to feed the population and to meet the demand of the increasing industrialization, urbanization, and various other things. And hence, this present study tries to assess and identify the various sectors in which water is being used and the emerging water demands of the area. We are trying to use remote sensing satellite data in this regard. The studies has been carried out in Jharkhand, which is a state having an area of 79,714 square kilometers. What you see is a satellite image of Jharkhand state, which we have cropped and merged together, and over it is a yellow boundary, which is the district boundary map of the state. And although this state boundary map has further been updated with Ranchi being divided into Khoti and Ranchi, so we have two more districts which has been aligned, but the map is not updated. I go to a bit of background of the study. When we try to assess the water resources of Jharkhand state, we try to understand the agroclimatic zones of the state. And when we try to understand the agroclimatic zones, the state is divided into three primary zones of agroclimatics, which is Western Zone, Central, Northeastern Plateau, and the Southeastern Plateau. But this is under Zone 4, Zone 5, and Zone 6 for Jharkhand state. And if you see the legends which are showing as characteristics, the green legend and the purple legend. So the green legend, you have the abbreviated forms of LWRC, UEDR, but the full forms are also available. So if you look at this agroclimatic zones, LWRC shows low water retention capacity. UEDR is uneven distribution of rain. HR is high runoff. NRC is no rabi crop. ES is eroded soil. LSF is low soil fertility. So basically, if you look at the characteristics of this, it has been mentioned. And in totality, if you compare the zones, zone 5 and zone 4 have the similar characteristics, and zone 6 has two additional characteristics apart from the rest four, which is eroded soil and low soil fertility. So in as when if you actually compare this or just try to assess the state of Jharkhand with respect to the agroclimatic zone, in it itself says that this region has a lot of natural problems associated with low water retention capacities and uneven distribution of rainfall, very high runoff. Why runoff is very high? Because it is a plateau region, and hence the water doesn't basically stay in the state, and it moves on to the Gangetic plain. Why we select Jharkhand was Jharkhand is an emerging state, and since it's in a state where a lot of planning process is going on, and we have influx of population going on with increasing industrialization, and so in this regard, the increasing population influx, high rainfall has been the primary factor controlling it. What is the need of the study? Basically, the increasing population and over extraction of water from over resources. I think someone's mic is on. Can you switch it off? Over extraction and exploitation is leading to the stress on the water resource. Then you have urban development that is occurring, and you have primarily Ranchi, Bokaro, Jamshedpur, Devghar, which is seeing intense increase in urban development. And we also have been facing drought every year, and Jharkhand government is claiming to get the subsidies for being a drought prone area, but because of certain natural issues, we have not yet been getting the benefit out of it. And then you have the increasing water crisis. Although the state has very high rainfall, yet every year the entire state faces water crisis. And hence we were trying to understand what are the natural reasons which is affecting the region. And hence the objective of the study was to study the water resources of the region, to understand the water balance, and to understand the trend by which the water resources are varying, and to identify the stress zones. So the whole purpose of this presentation was to identify the stress zones in the state of Jharkhand, and we are using GIS software as a tool to identify the zones. With respect to methodology, I adopted a method recommended by David Molden in the year 1997. He is currently the director of ECMOD, and initially David Molden was working with International Water Management Institute in Sri Lanka, and he has recommended this water accounting approach, which is a water balance approach. And his study has been very successful for some of the European countries, African countries, and in Sri Lanka. And what I did was I used his same similar approach and his similar tables to fit in the statistics or data that I obtained from the Jharkhand government. David Molden had initially suggested, with respect to water accounting, that we need to understand the inflows and the outflows. And so far, as a part of inflows, he divided the components of inflows into surface diversion, the precipitation, the river inflows, the subsurface inflows, and then the change, how the storages are changing, how the things are percolating. And then he also identified what are the where are the which are the sectors which are basically consuming water. So is it a process depletion or a non-process depletion? So basically, process depletion includes irrigation activities and municipal and industrial activities, whereas non-process depletions are both beneficial and non-beneficial in nature. And it may include your evapotranspiration. So all these are has to be computed over here. This approach is very significant if you get a lot of statistics, but with the scenario in case of Jharkhand, I was not able to obtain a lot of data, and hence some of the informations were blank. But still, with all the information that I had, I tried to commute the indices that were based on the specific components of water accounting. So these are the definitions which were primarily used in this study. For example, water depletion focuses upon the use or removal of water from the water basin that renders it unavailable for further use. Water available is the amount of water available for use, which is process, non-process, and utilization outflows. That means for industrial activities, for agricultural activities, and if there are certain waters which is going or percolating. What is the net inflow? It is the gross inflow plus changes in the storage. So these are the different definitions. Gross inflow is the total amount of water flowing into the river basin or defined area from a precipitation, river, or subsurface sources. Committed water is the part of outflows from the basin that is committed to the other uses. So from a specific river basin, if a specific amount of water is being consumed or is committed for a use, that's called committed water. Uncommitted water is the water that is getting depleted and is unutilizable. So those are all known as uncommitted water. process depletion focuses upon all the human intended activities that result in reduction in the water, and non-processes are all the natural occurring processes that are occurring in the depletion of water. For example, evapotranspiration. Now, there were certain indicators which are very important, and those were the depletion fraction, process fraction, beneficial utilization, and productivity of water. So basically, based on the table that I had shown initially on water accounting and their different columns and rows, uh, based on those figures, we have to calculate the four indicators which will be describing whether the status of water in a specific region. So our whole intention was to come to calculate these indicators. So if we see what is a depleted fraction, it reveals how much scope remains for the water resources to be developed. Process fraction, it relates to the process depletion to the total depletion. That is the ratio. It's the process depletion by total depletion. How much the water is getting consumed and of which how much is being as a process depletion. Beneficial utilization, it relates to the amount of water depleted by all beneficial processes, and productivity of water explains the quantities, quantifies the values derived from the water used. So what the moment we calculated this figure using this table. So if you see, we had the gross inflow of precipitation data. So we had that specific information. We also had the surface inflow statistics. So that was there. So after the sum, we came to know about the gross inflow. Storage information was not available, so that's a vacant column. Then you have net inflow becomes gross inflow minus storage, so that's the same as the gross inflow. Then you have the depletion information which was available. So we filled all those depletion information to calculate the final things, which is shown in column number 5. And then we calculate the outflows. So outflows was basically given as the uncommitted runoffs. So how much percentage is going off as runoff, that was provided, and then the seepage amount was also calculated in BCM. So when we with this table, if you see point number 10, its available water is 7328 BCM. So this was the entire statistics that we had obtained. Now based on this, we calculated the indicators. Now, these are the indicators, and for every indicator that we had discussed initially, we had the values as shown in column number 3. For example, depleted fraction is 0.103. Now, 0.103 is an indication of the fact that the region receives good inflow of water as compared to utilization. And according to this fraction, the region is safe and should not face water crisis because the ratio is quite less. Now, if you go for the process fraction, the ratio is process depletion by total depletion, which is 0.519, which is in an indication of that 50% of the depletion is due to the utilization of water, and remarkably, the equal amount goes off due to evapotranspiration and other natural method of losses. Then depletion fraction based on available water is 0.156, which indicates that approximately 15% of available water goes off as process and non-process depletion, and the rest 85% is unutilized. So this indicates that 85% of the water is going off as a runoff. Then we studied the process fraction for available, and then it indicates that only 8% of the available water is actual consumption. We generally have a tendency of blaming that it's the consumption is increasing, the population is increasing, because consumption is also increasing. And based on this figure, it shows that only 8% of the available water is the actual consumption in the region compared to the total water that is available. But the problem lies in serial number 3. If you see, almost 85% goes off as a runoff. So these are the indicators that we found based on the water accounting equations and methodologies. So we wanted to just use and compare it with the geospatial platform and see if we could get something out of all we can compare the results, if we can get something of stress regions and what is happening with the water resources. So if these are the inferences that we observed based on water accounting, and the region receives good amount of water, which is shown in the gross inflow. Available water is the sum of uncommitted outflows, non-depleted processes and processes. Almost 50% of the total utilization in the region is due to both process and non-process. Same as what we had discussed in the earlier slide. And water is actually consumed is only 8% of the available water. And according to Central Groundwater Board, the groundwater resource are only 21% utilized in Jharkhand state, and they are under safer category. But still, we are facing a lot of water crisis. So we need to identify where the problem is. Although using the methodology of water accounting, we have identified that it is the runoff which is basically playing a major role in case of water crisis. But we wanted to now validate this in a geospatial platform. So now we started to study the different geo-environmental parameters of the state. So we collected statistics pertaining to surface water resources. So all the major river basins and what is the total available surface water sources and geographical base area of that basin has been estimated. Then we went to prepare the entire drainage area of the Jharkhand state. This specific data has been used by AWIFS data. We used AWIFS data, which is a area-wide sensor, field sensor, and for this we digitized each and every stream and rivers of the state and merged them together in a single block. Now if you look at at one specific region over here which is having more white patches, that was because the resolution of that specific region was okay, but the cloud cover was affecting it and we didn't have a proper satellite data. So that is also shows, although we were able to track the entire water system, some region had problems because of cloud cover. And in case a specific satellite data has more than 15 or 30% of cloud cover, we should generally ignore that specific satellite data image. Now, this was the table that I had obtained for Central Groundwater Board, which categorizes the area as white if the stage of development of water is 65% and so on. And so we start step by step we started calculating and estimating what is the scenario existing in the Jharkhand state. Now this is also a secondary data which we obtained for the major contaminants which are found in Jharkhand state. And Jharkhand state is affected by fluoride, iron, arsenic, and nitrate. These are the primary contaminants which is found. And if you look at the yellow patches are the districts which are affected by iron and fluoride. So this is iron and fluoride statistics. Then you have blue, which is marked with iron, fluoride, and nitrate. You have red, which is having all the four categories like iron, fluoride, nitrate, and arsenic. So you have two districts which are having all the four contaminants, and iron is observed in most of the Singhbhum districts, Singhbhum, West Singhbhum, East Singhbhum, and Saraikela. So this was a water quality map. So if you see, even the water quality of the region is affected by natural contaminants. None of these contaminants are anthropogenic in nature. It's all based on groundwater studies where because of the natural processes, you have iron, nitrate, fluoride, and arsenic coming into the systems. So if a state is having 85% runoff, and if a state is having water crisis, and if a state is having a lot of water quality issues, so overall, it's a big question mark on the sustainability of water resources and its population dependent on it. So individually, now we started analyzing the precipitation, the groundwater, evapotranspiration, soil drainage, geomorphology, strata, morphometric analysis, and groundwater irrigation trend analysis. So we tried to assess all these things one by one. So with respect to precipitation trend analysis, we used statistics that was available for 47 stations across 1970 to 2002. The names of the stations are mentioned in the slide. And apart from 2002, we obtained the separate statistics for 2003 and 2004, because these were not based on stations, but these were based on single point source data for each district. So we have what I did was I separated these 2 years as a separate year, and did a combination study for 70 to 2002. Uh, when I prepared, this is a geospatial platform where the maps are prepared. So if you visibly see, it's more interesting to work in a geospatial platform, because at time it becomes monotonous to go through different tables and statistics and data. But the moment it comes as a pictorial depictions, so things become more easy to understand. When an average of rainfall was classified for Jharkhand state, it was observed that the state of Jharkhand during 1970 to 2002, and an average, it shows moderate rainfall in almost all the region, with few districts having good rainfall region. But as we shift from 1970 to 1990, in the next specific graph, it shows that the number of moderate region has increased and the number of good rainfall district has decreased. So this is a very interesting aspect which can be pictorially understood in a geospatial platform. So I think in this workshop you have been exposed to geospatial platform and GIS platforms. So maybe if you're aware of ArcGIS, and if you have worked upon it, so it basically has a Excel table which works and as a background, and where if you start feeding the information, you can multiply, you can play with the data and prepare multiple images. So this specific these specific images were prepared in ArcGIS platform. And when I compared with 1998 to 2002, a very important thing which came up was that a low rainfall area cropped up. So the good rainfall area completely vanished from the state, but the low rainfall area also came up, which were for the areas of Palamu, Garhwa, Latehar. So all these came up. For 2003 and 2004, if you recall, I just told that it was a single point data for the entire state for each district. So based on that, I prepared it, and the classification was followed similarly to what initially was suggested given. So for 2003, this specific image shows a good rainfall in few of the districts, low rainfall in the 4 districts, moderate rainfall in the shown by blue, and very good rainfall. Now, this was a specific year which had witnessed a good rainfall, and maybe this could be the reason why statistics varied, and hence it is actually difficult to understand the trend of a rainfall because it is a bit fluctuating. However, in 2004, again, the number of poor rainfall districts increased, with low rainfall district also have increased, and the moderate rainfall district is limited to 3, and good rainfall district limited to 1. And again, very good rainfall district has vanished. So a very good indication showing that since 1970, there has been a decline in rainfall as there is precipitation, and as a result, the number of districts facing poor rainfall has also increased. Um, so this is one indication of how the rainfall trend is changing in the state. So I already discussed the inferences that which areas are having higher and lower rainfalls, which is shown over here. So if you compare this table, the diagrammatic representations using GIS and the written components, it's always easier to understand and deliver things, or develop your understanding based on a diagrammatic representations compared to a written documents. So this is a very good comparison of showing why GIS is important, and remote sensing is a very good tool in replicating such things. Then we went for groundwater table analysis. So we use data for 555 sources for point sources for different years, 95, 2005, and 2008. And we used different borehole data almost for 555 sources for these 3 years. And based on these, what result came out, it will be shown in a diagrammatic, yeah, in this diagram. So if you see the plot, there is a change or decline in the groundwater table in almost all the district, but primarily Chatra, Gadwa, Gumla, Pakur are affected by severe changes in the monsoon in the groundwater table. And you have the season and year mentioned on the as a legend in this graph. So, and I think this is not very surprising because almost every district in the state or across the country is affected by the groundwater decline. So at times they will increase in the monsoon season, but while the time it reaches the summer season, there is a sharp decline in the condition. And this summer decline is going on in a faster rate. So we studied the crop evapotranspiration also now for the year 1970 to 2002, which is a 33-year span. And with respect to crop evapotranspiration, we were not able to infer specifically anything very strong. This was the plot that was obtained, and we plotted the rainfall and crop evapotranspiration, and but not major things could be inferred with reference to crop evapotranspiration, except that this is a part of depletion fraction, crop evapotranspiration. But something very interesting came up when we tried to understand other factors such as the soil drainage and erosion. Soil drainage refers to the outflows of water from the soil, and basically the natural soil drainage refers to the frequency and duration of the period when the soil is not saturated or partially saturated. Now, soil drainage is classified into 4 different categories, which is the poorly drained soil, imperfectly well, and moderately well drained soils. Poorly drained soil, they remain wet for several weeks during the monsoon, and it remains flooded for several weeks, but not the whole year. Imperfectly drained are remaining wet for several weeks during the monsoon, and water can stand for 1 or 2 weeks. Well drained soil, the water moves from the soil very quickly and does not accumulate in the soil. And moderately well drained soils are water may remain in the soil surface at a time for few days only, and then it will change. So if you basically see, we need to have soil characteristics which for maintaining the soil moisture and fertility uh, for a longer duration. So we obtained this soil map data from the National Bureau of Soil Science in Nagpur, and then we plotted those data in GIS platform to obtain this map. So once we obtained this map, it was classified into 99 categories. So this specific entire legends were classified from NBSS Nagpur, and they have typical basically we classify as fine sand, sand, silt, and clay. But NBSS Nagpur had given a very detailed classification based on the soil type. So all the way from its erosion potential, its water retaining potential. So each one of them had a different characteristics. So this map, which has 99 characteristics. Now to understand this information, we now classified on the basis of soil drainage. So same NBSS satellite NBSS map was now only we are trying to extract the soil drainage. So what is the soil drainage of that region? So if you see this specific image or the GIS map, it shows that the yellow color, which is prominent in this map, is well drained soil. Pink is poorly drained soil, and red is excessively drained soil. Green is imperfectly drained soil. Now, a major issue which is coming up largely is almost 80% of the state has no well-drained soil. That means water will not be staying in the soil for a longer time of period. And if you see what is required for water, maintaining the water moisture level in the soil is you need to have imperfectly drained soil or poorly drained soil, and those are less in number. So those statistics are very less. Now, based on this, we calculated the area percentage. So this was the area information that we obtained. For example, the soil drainage and erosion characteristics. So the well-drained soil is 9676 square kilometers. The well-drained is 40,000 square kilometers. Moderately drained is 14,000 square kilometers. Poorly drained is only 7,300 and imperfectly is 7,097. So out of 79,310 square kilometers, only 14,000 square kilometers of soil expansion area is suitable for water retention. The second category, if you look at the erosion table, this again shows that almost 80% of, in fact, 90% of the region is prone to severe to moderate erosion, whereas only 9,000 square kilometer of the region is prone to less erosion or slight erosion. Now, if you understand why Jharkhand state the fertility is so low, because it's highly prone to erosion, and since it is prone to erosion, so the agricultural practices were quite low in the region. However, now because of the initiatives that have been taken up by IARI and different agricultural organizations, we are happy to say that now multi cropping seasons are starting with water conservation initiatives taken up. But what the picture that I am showing here is about the natural condition of the state. But with respect to research and scientific developments, things are now changing. This was the soil erosion map. The data has already been shown in the previous slide. So if you look at this slide, the yellow patches are the region which shows less erosion, whereas other two are for moderate or severe erosions. So again, a very sad state of natural condition which exists in the entire state, where the erosion potentials are also very high. So we try to prepare the drainage stress map. So when we try to prepare the drainage stress map, it was based on the factors of drainage and factors of erosion. So if you look at the specific map that has been prepared, the GIS platform, so the black patches show imperfectly drained with moderate erosion or poorly drained with moderate to slight erosion. So these are basically safer zones, and those red patches are unsafe zones or more stressed zones. So the picture that I'm showing here is about the erosion potentials and the erosion potentials are Am I audible?
So you are audible, but your screen is not visible.
The screen is not visible. Just 1 second. Maybe I will disconnect and again I will join. Maybe there
Yeah,
was
yeah, sure,
some
sure.
there was some internet issue right now.
Yeah.
Is this visible now?
Yes, it is visible now.
Okay. So in the last two slides, I hope because of the internet issue, it didn't. I don't know whether you were able to see it. So in the last two slides, we had discussed about the erosion and about the drainage. So we showed the two factors of how the drainage condition is going on in the state, and then how the erosion is going on in the state. So almost 80 to 90% of the state is prone to high erosion and high drainage. So we prepared a drainage stress map, and if you look from red to black, as the legend shows, the stress is decreasing, but the area covered by major stress area is very high. That is what I was trying to discuss now. Is when you have in a GIS platform, the only hurdle is the moment you prepare the Excel sheet, or the moment the database is prepared or information sheet is prepared, as GIS stands for Geographic Information System. So once the information system is created, you have the ability to play with those information and create multiple layers of maps, which could be easy to understand and which you can change according to the needs of the researchers or decision makers or policy initiatives. Those can be changed accordingly in a very easy way. And the updation is also very easy. You can go for a very good comparisons of information. So those are the plus points of working in a GIS platform. If you look at this table, which has been obtained from the initial previous map, if you look at this data, which shows that excessive drainage area and moderate erosion is 1600 square kilometers. Moderate drain and moderate erosion is almost 1 lakh 22, 12,021 square kilometers. So in totality, it's a very grave situation naturally in the state of Jharkhand, which is prone to multiple layers of associations of problems. So when we added the rainfall trend over it, this was a picture that we had obtained, and this is also a very interesting aspect of overlay, where you can overlay multiple layers over each other, and you can go for making them transparent or translucent or make giving them different shades. So the application is very easy to understand and to see how the changes are occurring. So if you see the rainfall patterns, which I have tried to overlay on the stress map, only two districts are not showing low rainfall region, whereas entire state is showing less rainfall region. So if a state is having issues pertaining to its natural conditions with respect to erosion, with respect to drainage, and with respect to precipitation, it is but obvious that the condition of water resources are declining in a very negative manner, and we need to now focus on more positive impacts of human activities. And research is something which keeps on helping and adding benefits to the society. And if you can see, this is the condition of state, and it's a very good work given by so many scientists working in different areas, and things are getting replicated in the state. And so at least the food insecurity is not so much as compared to the water insecurity in the state. We also went for strata analysis, and in the strata analysis, we try to understand what is the characteristics of the topsoil, the layers which were observed in the bottom layers. We obtained this data from the geological survey, and it shows multi layers of rocks. Like topsoil is deficient of organic matter, phosphorus, and nitrogenous matter. Well, it is followed by granitic, quartzite, and granitic is basically impermeable in nature, and quartzite is again a hard metamorphic rocks. So multiple combination all the way from fluctuating rainfall to soil which is not good for erosion, not good for agriculture. Then again, the layers with the rock strata is impermeable in nature, and only we have few fractures through which the groundwater is getting recharged. So it's almost like staying in a condition where you have less rainfall, followed by surface water declining, followed by groundwater getting contaminated with arsenic and fluoride, and a soil system which is not supportive, a rock strata which is stopping the water for percolating. So a very unique condition comes up for the entire state, and to understand how things can be managed. And I think, but because of scientific advancement and utilization of water conservation techniques, and use of proper agricultural practices, things are still being managed in the state quite well. This is the geomorphological units which are present in the state, and you have multiple layers of unit. This I also obtained from one of my friends who was a geographer, and they provided me all these informations. And if you look at some of these patches, these are again not very suitable for water recharge. For example, the plateau region is almost covering the 70% of the state, which witnesses high runoff. Then you have denudational hills, structural hills, which are all indication of some kind of erosion going on in the state. So natural features which are prone to erosion or which come up because of erosion. It's only the light blue patches where the water gets percolated, or which are the zones of recharge. So hence, naturally, the state is affected by multiple factors. So if you look at the groundwater prospects of each of the units, I may not be able to explain or define the units over here, which is not basically my domain. But if you look at the second column, which is the groundwater prospect, which I was trying to understand. So you have alluvial plains, which are quite limited, but good to moderate prospects, and floodplains, which again have good to moderate. But rest all, if you see, it is poor to moderate, and in fact, some of them have nil groundwater prospects. So naturally, the state has many issues pertaining to water resources. This is how my results of use in a geospatial platform shown through maps and statistics and based on water accounting are all matching with each other. The only difference is that when you show a thing in a text form or in a tabular form, it may not be very interesting to look at, or maybe not be very interesting or easy to understand. But any form of replication of information which is more pictorial is highly influential, and people are easy to understand. And that is why if you see among the ICT tools, which is the communication tools adopted globally, you have these banners which are very successful. You have these Nukkad Nataks which are very successful, or you have these pamphlets having diagrams which are very successful. In case of Corona also, when you depict it through a diagram and its impact in a video through a video. So those are more impactful compared to normal written matter. Hence, I think this is a quite a good workshop that is being intended to showcase or highlight the importance of remote sensing, GIS, and Python. And I think that's all from my end. This is my overall summary of the research work, but I think I may end over here now. If there are any specific questions from the participants, I will be happy to share my ideas. In fact, it will be good if any one of you can also share your perspectives of remote sensing and GIS. Thank you so much. Am I audible?
Hello, sir.
Yeah.
I have a query just for remote sensing satellite data image analysis for the groundwater storage enable change. Because your study is mostly in concentrate or GIS, is it possible? But in recent many limitation of the satellite image like coarse resolutions because GRACE mission or GLDAS mission or many routing SWAT LSM land surface model for use this analysis for this groundwater storage anomaly change in recent years. Is there is any scope for in this region?
See, basically, resolution plays an important part, that is for sure. But resolution is an important part when you're dealing with the optical remote sensing. So when you go for surface studies, then in that case, it's optical remote sensing plays an important part, and the resolution comes into action. But when you're talking about groundwater anomalies, then in that case, I think if you focus upon microwave remote sensing, that will be more beneficial.
Okay, sir. Okay.
Okay, then. Thank you so much. Should I end the meet? Thank you, madam. Okay, then. Thank you so much. Thank you, participants. I will take leave. Thank you for having the patience, and very happy Deepavali to all of you.
Kachri ma'am, should we leave now? Is the class over for today? Hello? Hello? Kachri madam, are you there? Please tell us whether the class is over for today or not. Should we leave now?